All right, welcome to this high-yield explainer designed specifically for your DPE exam preparation. I'm absolutely thrilled to be guiding you through this material today. We're going to take some fairly complex computer fundamentals and transform them into, well, visually digestible concepts. Whether you're an FSC student, a DPE candidate tackling the general paper, or maybe you're just looking to solidify your technical foundation, you are in exactly the right place. So let's jump right in.
Before we even touch the technical architecture, ask yourself a fundamental question. How does a piece of silicon, copper, and plastic actually understand what you are typing right now? I mean, hardware on its own is just dormant circuitry, right? It needs a master translator. It needs a system to bridge the gap between our human language and the electrical impulses the machine actually relies on.
Here is our roadmap for today. We'll be covering 1. The central system controller. 2. Kernel and shell architecture. 3. Managing processes and memory. 4. The boot process. 5. Databases and structured data. And we'll wrap up with 6. A high-yield exam review.
Okay, let's start right in with Section 1, the Central System Controller.
For your DPE exam, you've got to remember that the operating system, or OS, is essentially the ultimate micromanager. It's the software allocating memory and deciding which tasks get priority so that multiple programs can run simultaneously without just crashing into one another. Think of it like a really meticulous school administrator managing resources so every single department runs smoothly.
Think about the translation process here. When you press the letter A on your keyboard, the OS instantly steps in. It takes that keystroke and converts it into a special binary code, just zeros and ones, specifically 01000001. This code is then sent to your computer screen, which displays the A. Now, this happens so incredibly fast that it feels instant, but without the OS acting as your personal translator, the hardware wouldn't have a clue what to do with that input. Moving deeper into the system, Section 2, Kernel and Shell Architecture.
Notice the clear division of labor we have here. At the very core, we have the kernel. The kernel is the engine. It's directly controlling the computer's system software and hardware, like the CPU and memory. Surrounding that is the shell. The shell is the steering wheel and dashboard that you, the user, interact with. That could be clicking icons on the graphical desktop or typing in a command line terminal. So you talk to the shell talks to the kernel, and the kernel actually drives the hardware. So how exactly do your applications communicate with that highly protected kernel? Well, to bridge the gap, programs use things called system calls. These are essentially secure requests to the OS to do something the program just isn't allowed to do directly. You should absolutely memorize these for your upcoming test. We've got open, read, write, and particularly fork, which the OS uses to create a brand new process by duplicating an existing one. It's exactly what happens when you open a new tab in your web browser.
Let's move to Section 3, Managing Processes and Memory.
Every single task running on your computer is called a process, and each one has a very strict life cycle. Think of opening that web browser again. First, the OS creates the process by loading the program from your hard drive into memory. Second, it executes your tasks, loading web pages, playing videos, whatever you're doing. And finally, when you click the X to close the window, the OS steps in for termination. It shuts it down and frees up those crucial system resources for the next task.
But what happens when multiple processes are begging the CPU for attention at the exact same time? Well, the OS has to use scheduling. Here's a classic numerical example of first-come, first-served scheduling. It's essentially treating the CPU like a queue at a shop counter. As you can see, we've got process 1 arriving first, needing 5 seconds. Process 2 arrives a second later, needing 3 seconds. And process 3 arrives at the 2-second mark, only needing a quick 2-second job. So the absolutely crucial point is how this plays out on a timeline. Process 1 hogs the CPU for the first 5 seconds. Process 2 and 3 just have to sit there and wait. Notice the trap here? It's known as the convoy effect. Even though process 3 is the shortest, easiest task, it's stuck waiting a very long time behind larger tasks simply because it arrived slightly later. It's a fair system for sure, but definitely not always the most efficient. Now, all these active processes need a place to live, which brings us to memory management. A major distinction for you DPE candidates is understanding primary versus virtual memory. RAM is your primary workspace. It is blazing fast but temporary. But when your RAM gets completely full because you have way too many tabs open, the OS cleverly borrows space from your slower storage drive. This acts as virtual memory.
Just remember, relying too heavily on virtual memory reduces overall system performance because hard drives and SSDs simply cannot match the data transfer speeds of pure RAM.
You know, your OS pulls off an incredible magic trick every single day. While multitasking is what you experience as a user, like listening to music while typing up a document, concurrency is the high-speed illusion happening behind the scenes. A CPU core can literally only do one thing at an exact given moment, but the OS acts like a master chef rapidly switching between 3 different dishes on a stove millions of times a second. It's so incredibly fast that to our human eyes, it looks like simultaneous execution.
Next up, Section 4, the boot process.
When you hit the physical power button, special software permanently built in your motherboard called firmware kicks into gear. Older systems use BIOS, which give you a basic, kind of intimidating text-only menu. Modern computers use UEFI, which is faster, more secure, and actually supports graphical menus with mouse input. Either way, this firmware's very first job is running the post, the power-on self-test. This ensures critical hardware like RAM is present and working before it even attempts to load the operating system.
Now, if that startup process fails, or if a running application crashes later on, your OS doesn't just throw its hands up and give up. It keeps meticulous records. Built-in tools like the Windows Event Viewer act as an investigative logbook. It records detailed logs of system activities, warnings, and error messages, which is absolutely vital for system health monitoring and troubleshooting.
Moving right along to Section 5, databases and structured data.
When you start dealing with massive amounts of data, a simple spreadsheet just won't cut it anymore. When raw information is cleaned and validated, it graduates into a structured database. This allows for multi-user access, reduces data duplication, and makes searching highly efficient. The hierarchy here is key. Databases hold tables. Tables hold individual rows called records, and each record is broken down into specific columns called fields.
Let's apply this to a real DPE exam scenario. Say we have a database of chemistry flashcards. Each specific flashcard, like one asking for the empirical formula of a compound, or one calculating volume at standard temperature and pressure, becomes a single record or row. That record is then beautifully organized by fields or columns, such as topic, the content on the front of the card, the back, and even metadata like its difficulty level on Bloom's taxonomy.
To retrieve that specific advanced chemistry flashcard, your database management system relies on SQL, structured query language. Instead of manually scrolling through thousands of entries, you use simple, powerful commands. A query like select all from chemistry_flashcards where difficulty equals advanced tells the OS exactly what to pull from the file system. It is precise, it's efficient, and it's incredibly powerful.
And finally, Section 6, our high-yield exam review. Go ahead and screenshot this slide right now. This is your ultimate high-yield checklist. Just to recap, the OS is your translator and central resource manager. The kernel is your engine, while the shell is your interface dashboard. Remember that first-come, first-served scheduling can cause that pesky convoy effect. Virtual memory is a lifesaver, but it's really just a slow backup for your RAM. And finally, robust databases use SQL to organize data into strict tables, records, and fields. Connecting these core concepts, literally from the initial system call in the shell, all the way to storing a SQL database record on your NVMe drive, that is the absolute key to mastering computer fundamentals.
I want to leave you with this final thought. We've spent this explainer detailing a virtually perfect, logical system to process hardware requests and store data safely. But modern computing relies heavily on artificial intelligence analyzing that data. It really makes you wonder, if the raw data we feed into our perfectly structured SQL tables is flawed or dirty, can we ever truly trust the automated outputs it generates? It's just a really interesting reality to keep in mind as you continue your technical studies. Thanks so much for learning with me today, and best of luck on your DPE exams.